I was starting to wonder. I was like, where's. Switched it up on y'all.
You're matching Marianne this term.
What?
You're matching Marianne this term.
How so?
Her 222's in here as well.
Oh.
In the same math classroom and at the same time.
Oh, that's funny. I was beginning to. I was like, she's never late. Yeah. I am.
Everyone in the other class is like, sit down, scrub. And I'm like, oh no, we're just in the wrong place.
That's funny.
I heard that class is really hard. Chelsea told me it was really hard.
Yeah, well, I think the problem is it's marketed as like a 100 level class, and then you have to do math, so people.
She was like, I had to memorize all these formulas. It was ridiculous.
That's funny.
Everything okay with the letter?
Oh, yeah, I'm gonna.
Sweet. I'm
But
gonna go. I needed two. I didn't realize. They sent me an email. They're like, it'll be a recommendation letter. I'm like, cool. I already have someone.
yeah.
And then they're like, it has to be from your school.
Oh, no.
Say that in the email.
Yeah.
When I got to that page. And I needed two, and I was like, damn it.
Oh, my gosh.
Thank you.
Yeah. I'm gonna.
I'm gonna get Anna to do the other one.
Nice. Yeah, I'm gonna finish it up today. So, yeah, I want to submit it like tonight. So it's. And then you can double check and like yell at me on Thursday if for some reason it's not in. But yeah, it should be in by tonight. I just like to give myself buffer time too. Like,
Just have time to complete it, and then like Sunday night.
yeah.
Oh, I got all my essays done. I was like,
No, that's
nice.
awesome.
I was like, I actually am gonna be able to get this in. And it's for up to $55,000 a year.
Wow. I feel like we have more people.
Trying to buy that fancy TI emulator software is such a pain in the ass.
Wait, are you trying to find the same calculator I use?
I found it. Just trying to get the licensing for
Oh,
it.
it should just be free. All right. Are we all here today? So welcome. So yeah, we did switch rooms. I double checked the schedule myself, so I wouldn't end up in the wrong place. So let's start off with attendance. Again, y'all who know me know that I normally don't take attendance, and we'll go over some things because there are some new faces in the crowd that I don't know. But yeah, let's take attendance before we jump into things. Jules back there. Bernardo, there you are. Juan, I don't know you. Juan with a B. Okay, moving on. Christian, another person I don't know. Christian Carlson. Okay, moving on. Alex, I know you. Happy, where's Happy today? Okay, I don't see Happy. Dyson, I thought I saw you. Where are you at? Is Dyson here? I swear I saw him like floating the halls. All right, Finn, you're back there. Ellen, Grace is somewhere. Tyga, there you're at. Gabe with an F. Thank you. Ari, there you are. Gabe G. Kat. Okay, person I don't know, Shane. Nice to meet you. Naya, where are you sitting? There you are. Jada. Nice to meet you. Leanne, there you are. Malathi is here. I saw there you are. Skylar, where's Skylar sitting? Amelia, nice to meet you. Joseph with a K, nice to meet you as well. Max, Matthew. Oh, hang on, Matthew McVeigh, and then yeah, Matthew. All right, Brooks here. Sorry, Alana. Joanna, is Joanna? Yeah, there you are. Hector is Diego, I saw you. Cohen. Ian, I saw you wandering around. There you are. Alexis, yes, saw you walk in. Max Terse and Gavin. Excellent. So we're missing a few people. Sorry, was Bernardo here? Maybe he didn't walk in. And then Juan, are you Juan? Okay, sorry. Missed you. And then did Christian walk in? Christian Carlson, so still negative. Okay. And then Happy and Dyson didn't show up. I didn't miss them. Okay. I don't know where they're at, but I assume they'll join us. Perfect. All right, so that's attendance. And then hopefully, if you're new to the party, you have signed up for a lab section. And so we have lab either Tuesdays or Thursdays. And we do start lab this week. Luckily for everybody, so this week's lab is a computer lab. So that means there's just no hazards. Next week, I can't remember what the lab is. Let's look at the syllabus. And so where's my syllabus? Sorry, too many windows already. So syllabus. Oh, there's Dyson. We were looking for you. All right. So blah, blah, blah. Pretty much the same story as last quarter. Again, those of you who have had me, we're still using the same book. So I would recommend purchasing this book. I think some people know how to get this book free online. So if money is a hardship, you can maybe ask your classmates. There's also the OpenStax resources. So I don't know if you guys are familiar with the OpenStax book. You can just Google like OpenStax. The problem is this book is not sufficient for this class. It's a great helpful introduction, but it is not to the level of this one. So again, obviously this is a preferred one, but you could always check that out as well. And then, so we will provide goggles for you guys. You don't have to worry about that. And then do bring a calculator. And so you want to bring your calculator all the time so you can practice. I need to fix my syllabus since there's no more recitation. So similar percent of weighting. Again, don't forget these reading questions. So the reading questions are found in Blackboard. So that's the only thing that you need to do on Blackboard is reading questions. and they are under our assignments, and I apologize that the date is probably off. I haven't like fixed every little detail. And then reading questions are here, and that's all you need to complete online. And so I hand out, right, the homework that's going to be due. So the homework is there. And then you also have the lab packets available. And so I just hand out the lab and the homework of the week. And so you can see our schedule. And so typically, right, we lecture all of Tuesday. And then you may or may not have lab that day. And then Thursday, we typically kind of take a quiz. This week will be like a welcome quiz that you won't have to study for. So just, are you looking for chemistry? Yeah. Okay, yep, we're in here. Are you Christian? Yep. Awesome, finding my missing students. Okay. And so then we'll have I'll lecture for part of Thursday, try to do a demo, and then do our typical quiz, and then the rest of that time can be used for questions or homework and so forth. And then we just kind of repeat that pattern. Again, if you've been in my class, you kind of know that. And so next week, atomic weight of magnesium. You will want to wear cotton clothing with that lab, so that probably involves flame, if I remember correctly, or acid. So typically, for lab, and we'll go over this today in lab, but you always want to wear long pants, which shouldn't be an issue, hopefully in the winter. So long pants, closed-toed shoes, and typically cotton if we have a flame hazard, but it is good practice to wear cotton clothing. And so then we can look at kind of our schedule. And so I like to tell people too, because some people either love or hate kind of the first 2 weeks. So it's pretty heavy with the MO theory, a lot of geometry. So this week we're going to start with geometry, and we'll get into that. It'll be a good review, and it'll be good for people that are joining the class, because then it's a good refresher on how to draw Lewis dot structures. But then we'll take it a step further and start looking at our orbitals involved. Week 2 is going to be more intense with MO diagrams. And this is where I tell people, just hang with it. Like, there are some people that absolutely hate this, and then they want to just drop the class. But I'm warning you, you will completely switch topics. So don't worry. If you completely hate MO theory, just hang with it, and we will go back to algebra fun. And I think a lot of people are pretty good at the algebra. So if that's more your style, we'll get back to all that later in the quarter. We'll go back, chemical kinetics, equilibrium, yada, yada, yada. But it really is just the first 2 weeks that are a little different. And so don't drop the class or anything like that in the first 2 weeks. Just hang with the course. And then, just other things on the horizon. I'll talk about this later on Thursday. So those of you who were in my class last year, or last quarter, we're going to be working towards our research paper. So of course, some of you guys, right, you kind of looked at a topic, explored a topic, and then we're just going to continue that. So picking our topic, if we liked it, solidify it, and then eventually we'll have our draft paper due. And so our paper draft, but like I said, I'll go over all that, the requirements at the end, but just kind of building towards our project. Questions, comments? So you can look at the syllabus in more detail.
Sorry, I'm just having a hard time finding the syllabus.
Oh, it's called Concourse at the very top. Sorry, I forgot to rename it too. Other questions, comments? All right, let's dive into it. And so hopefully you picked this up, or maybe you still have yours from last quarter. So now we're going to be kind of looking at our shapes again, and kind of really diving into our orbitals. But let's do a quick refresher or recap. And so let's kind of recall our orbitals, or our basic shapes. So we have our s orbital. So what does the s orbital look like? So in sphere, and I pulled up some pictures, just so again we can put ourselves in the correct mind frame, and a little refresher, especially for those who did not have me last quarter. And so, yes, a nice looking sphere. And then our p orbitals. So what do we say those typically look like? Yeah, balloons, dumbbells. So yeah, if you're into like balloon shapes, and twisting, and so kind of our dumbbell shape. And then now I'm going to slightly refine the picture. So this is our shape, but then we want to highlight that we have these nodes. And so this is shaded. And so they always have kind of opposite shading. And I'm going to call this PX. I'm going to call this PZ, so up and down. And then PY is coming in and out of the plane of the board. So again, opposite shading, so that will become kind of relevant now. And just a quick refresher, we're not going to really get into the d orbitals right now, but at least we'll look at some of them so we can have some of them in our mind. So dz squared is typically this like donut dumbbell shape. And then the shading on it, so shading does matter, is the inside is one color and then the outside donut ring is the opposite color. And again, I'm just using the either shading or lack of shading to show that. And then typically our other d orbitals kind of look like so. And again, I apologize that I'm not the greatest artist. But they're basically like this, but then in all, right, the planes. But again, kind of paying attention to that shading there. So that'll be potentially relevant later. All right, so let's do a little refresher now, or kind of we're going to start with our geometry shapes. And so kind of my goal and what we're going to do is we want to go through each one of these groups here, right? So we'll start with our linear and kind of hit typical examples, practice drawing our Lewis dot structures, and then we'll also see the hybridization that's involved so we can very quickly see this, especially when we move on to OChem. And so let's call this, I'll call this my 2 electron group. And so this is a good refresher. So see if you can draw your Lewis dot structure for beryllium chloride here. And you could perhaps note some oddities about this, but so just try to draw out what do you think your Lewis dot structure is, right? How many electrons are in the party? What does it look like? Okay, I'm seeing some good shapes. I was just checking out there. And so let's just go through it together. How many electrons did beryllium bring to the party? And then how much does each chlorine bring? So 7 times 2, 14. So we have 16 electrons. And then most people ended up with a structure that looked like so. And so there's our electrons, right? 1, 2, 3, 4, 5, 6, 7, 8 there. And then obviously another 8. So 8 plus 8, 16. So that is indeed our structure here. And so now, and I built a little molecule of it too, right? And so anything strike you odd about this? Didn't feel odd to you at all? Or, well, in this case, less, right? Maybe hypovalent. I didn't hear what you quite said. So yeah, this is odd. And so let's look at a few things. So yes, it is electron deficient here. So beryllium is only filling 4 electrons, so that is odd. I was wondering if anybody just felt uncomfortable that it was a covalent compound. And so I did want to point out, so this is from gas phase calculations, this beryllium chloride. And I did want to pull up, again, our structure here. And so it does say that in the gas phase, and that's typically what we find is when we're doing these kind of geometry structures, this is truly in the gas phase when it exists as a monomer. And given that they reported on it, that means there's some sort of evidence for this. And then I did want to point out, right, that it's kind of similar, at least in name, to like calcium fluoride or strontium fluoride, right? Kind of, you might assume it's an ionic compound, but it's not. And again, right, this is only based off of experimental data. So again, they had to isolate it like this. And I did want to point out, right, so calcium fluoride is truly an ionic compound structure. And we can tell that, again, by the actual packing structure of it. So it has, again, a completely kind of different structural form than our beryllium chloride. And then kind of to the point of beryllium being electron deficient, we find that it also does this weird dimerization often. So that's what's shown here, is this weird dimer compound. And of course, right, that's to help stabilize our beryllium and give it an octet. So that's interesting. All right, let's look at how we make our bond then. And so again, right, we're kind of now imagining our orbitals. And so this is called this geometry here. And we can, eventually we'll write our little cheat sheet. So I'll start by writing it here. So anytime you see this 2 electron pairs, we know we have what's called sp hybridization. And so, yeah, you might want to mark this on your sheet, but then I'll go back to our group 2 so we can figure out, well, what does this truly mean? And so when we have sp hybridization, we're saying that we have one s orbital and one p orbital, and they kind of come together to give us, right, our sp hybridized lobe here. So it's kind of fat, and then we'll get our shading properly. And so, right, that's in prime condition. And we're just, again, we're trying to essentially do math. So the whole point of like this structure is, right, normally Schrodinger equation, blah, 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 try to solve it, right? That's what you can do in physics. What we're trying to do is we're doing, right, Schrodinger's equation, but just using our pictures and math, and that's why the shading matters, to really show these complex things in what I call a back of the envelope, back of the napkin calculation. And so these are, again, super powerful when you're trying to like come up with a research idea or figure out what the heck happened. And so then, so that's what's going on. And so now we're looking at our orbitals involved. And so our chlorine, so this is going to be more, so chlorine, right, is going to be centered on a p orbital. So that's what's bonding, again, in that direction. But then what we care about is their orientation. So right, they're kind of what's called head to head there. So really, right, the orbitals are next to each other. And they should be, sorry, let me get my shading correct. So they should be what's called in phase to bond, aka the same shading pattern. And so now this is showing our bond here. So I'll kind of redraw this, right? So we're just kind of drawing the orbitals on top and showing that this bond is a sigma bond here. And so that's pretty typical. So right, when you have a single bond, it is generally a sigma bond, again, that head-to-head interaction. And so this would also be a sigma bond on this side. So we can say, right, we have 2 sigma bonds total here. So let's try another one. So see if you can draw the Lewis dot structure for CO2. So what does that look like? Double bonds. Try that out for a second. Right, what do our drawings look like? Looking good. So they look pretty good. I was just looking around. And so it looks like everybody made these pretty symmetric looking structures. So again, fill in all your electrons. What can we say that's interesting about boron here? So boron is electron deficient once again. So it's only feeling 6 electrons, so 6 valence electrons total. And then obviously these compounds tend to be pretty reactive. So again, that's what we're trying to see with our geometry as well, is like what's going to happen, what do we predict? And so since boron is electron deficient, and you can make many other compounds like this, so aluminum trichloride, gallium trichloride. So those are all pretty similar. And they all have similar properties too, in the fact that they're all angry fuming either. So boron trichloride is an angry fuming liquid. And then like aluminum trichloride is an angry fuming powder. And again, they're just reacting with the ambient kind of water in the atmosphere to make a boron oxygen bond or aluminum oxygen bond and become electron, satisfy the octet rule. So let's look, and so again, right, we'll say sp2 hybridized. And then we also want to identify our geometry. And so that's what, again, this cheat sheet is good for. So looking at it, so what's our geometry? So trigonal planar, and then again, right, use your cheat sheet so it tells you what angle they all have. And so trigonal planar, so this one is at least fairly straightforward. But then note, right, our typical geometry of 120. And so it should be, right, even all around. And then obviously, again, if you're doing like research or something, you'd be looking for any sort of distortions in this angle, any sort of breaking of the expected symmetry. Let's try another one. So draw out the Lewis dot structure for SO3. I mean, we could.
I was just wondering if I should leave space in my notes or just.
I was probably going to move on, but if anyone asked, I would do them.
Let's draw. So if we could make a double bond, so this is okay for sulfur. In fact,
So what do we get for sulfur trioxide? So it'll look like. Might be a few right answers too. So you could draw one, right, with all double bonds. And so that is indeed one correct Lewis dot structure. So let's see, how many electrons are in this thing? So 6 times 4, 24. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So that's one structure. And then what's kind of odd about this one? So now it's hypervalent, so not out of the question for sulfur. So then we could draw a valid resonance structure. And so this one, right, minimizes formal charges. So hence why I didn't draw any. But then you said one double bond, correct? So then we can minimize our hypervalent. So right now satisfying the octet rule. But then we will have some charges, so that's fine. Do we need a refresher on formal charges? So please, okay. So formal charge, so let's write the formula for formal charge. So that's just the number of valence electrons, so right from the periodic table. Yeah. Oh, yeah. So, minus the number of bonds. So again, that's individual bonds bound to it, minus, and I put number of individual electrons. So then for sulfur, I'll write it out. So sulfur then, in this case, right, so 6 valence electrons normally, minus 1, 2, 3, 4 bonds. So that's how I got the 2 plus charge. And then, right, neutral molecules, so we know that we have to find our negative charge somewhere. And indeed, right, it is on our oxygen, the ones with the single bonds. So 6 minus 1 bond minus 1, 2, 3, 4, 5, 6 electrons gives us -1 for both of those. And then again, right, adds all up to 0, so that's good. So yes, another valid resonance structure. And obviously you could rotate the bonds around. So all of this is to say, right, the connectivity doesn't matter. So as long as there's one bond, right, there's one line, then it still falls under this trigonal planar, right? So it's still trigonal planar. We're not changing the geometry by moving this double bond around, right? You're just kind of shifting electron density truly, right, and shifting that pi bond. And so that's something else to kind of note, especially, right, as we get deeper and deeper into chemistry, or hopefully you guys move on, but even if you don't, right, it's something to appreciate that you typically don't break sigma bonds, right, but then you can move your pi bonds around and that electron density can shift around. Does that make sense? So then our geometry, so again, it's still trigonal planar, and still, right, we'll say our center then is sp2 hybridized still. Again, it doesn't matter here. And then obviously, depending how you draw it, right, you can kind of formally say, well, the way you've drawn it here, obviously, you have 3 sigma bonds and then 3 pi bonds. But again, right, you can kind of shift that around whether you make a pi bond or not. And we'll keep, like I said, we'll keep kind of looking at this and see this pi activity. Questions are still okay. So let's try another one. So let's do SO2. What do you mean? Like, we could keep making resonance structures.
No, I mean a resonance hybrid, where you like combine all the resonance forms.
I guess I'm not understanding what you're. Oh, like you just want a dash line there instead? Yeah, I mean, that's just like a shorthand way of drawing that, right? Yeah, I mean, so I guess, right, you could draw something kind of like this. Is that what you mean? Yeah. So that would be fine, but yeah, kind of like what she was saying. This is just kind of a more general saying, like, yeah, you can play around with the double bonds, but this one just doesn't like show us anything that precisely. So it's better for like electron bookkeeping and everything to kind of draw it one or the other, right? This is kind of like a more shorthand of like a teaching thing, if that kind of makes sense, the distinction. All right, so try SO2 for a second. How's our SO2 looking? SO2. So yeah, SO2s look like they're coming along. And so I'll just kind of draw what I saw. So something like this is what I saw people drawing. And so now let's look at a few things. So what's its hybridization? Yep. So yeah, we're still in sp2, right? So that's good. So don't forget these lone pairs. We make them a little darker. Yeah. And so yeah, so like going back to our sheet, so yeah, like he just stated, the 3, right, does count for electron pairs. And so that is what we're looking at then, right, with this geometry. So bent. And so sometimes you also call this one, so this could be called V-shaped bent. Oops, V-shaped bent. So this is obviously to distinguish it from water. So later, right, as we progress down our little groups, we'll obviously get to water, compare how that has 2 lone pairs. So that does give it, right, a slightly different angle. And so that's also, again, what we kind of want to take away with using the sheet. And then this can also tell us things. So, right, our lone pairs then occupy more space than an atom typically. So, right, they're forcing down more repulsion. And so that's why, right, this angle is a little bit smaller now of 119 versus, right, the 120. So that's pretty cool. So that's, right, telling you, again, the power of that distortion. So again, your lone pairs pulling these just a little closer together. So V-shaped bent, 119 degrees. And then, so other terms that we want to add now. So like we mentioned, so it's sp2 hybridized. So that means its electron geometry is still trigonal planar, right? Because it's our 3 family. And electron geometry is again looking at our orbital placement. But then the molecular geometry is where we can use that term V-shaped bent there. So that looks good. And again, right, if you wanted to just kind of think about what orbitals are involved, maybe let's do that for good practice. So let me kind of rewrite it for a second. So S, O, right? And then you can kind of start doing this a little faster here. And so what's our hybridization on all these three actually? Yep, so they're all sp2. So right, we're just kind of drawing out our orbitals then. So our lone pair's in one of those. Again, right, they're all meeting head to head everywhere. They're head to head. We have a sigma bond. So sigma bond, right, lone pairs in there. So just again, this tells us where our lone pair is. And then, right, we can tell what contributes to our bond. So again, we have, I'm going to call it py. So our py orbital, again, going up and down here, and we can see how we have this sort of pi interaction, right, all throughout here. So again, that pi, so through space, again, they're all in the same shading. So giving us our pi bond there. So pi, pi. Does that make sense? Feeling okay about this?
So the best way to think about it is like the first one going out would always be sigma, and the one where it's returning is pi.
So the head-to-head one is a sigma, right?
Yeah.
Yeah.
You can only have pi when it's a double bond.
Yeah, exactly. And then, yeah, the pi is the through space. And then they have to be the same shading though, right? So the tops both have to be either shaded or unshaded, right? So once they flip shading, then it's not a bonding interaction. All right, let's take a little 10-minute break there. So again, if you haven't been in my class before, that's typically how we do it. Take a little 10-minute break, clear your brain a little bit, and then we'll be back in 10 minutes to keep lecturing. All right, so let's just keep going down our line here. So now we're going to start our 4 electron pairs. And so as you can imagine, right, that's now sp3 hybridization. And so let's start. So 4 electron pair group. And so I'll just start with our AX4. So meaning, right, 4 atoms. What's a good typical compound? You should know this. Methane, yeah. So go ahead, right, take a second or two to draw out methane. Other ones, right, carbon tetrachloride, silicon tetrafluoride, etc. You go crazy, but what does that look like? Draw it out. And so again, right, we have our sp3 hybridization. And so now it's going to be s plus our 3 p orbitals. So px, py, pz. And so that gives us, right, our typical tetrahedral shape. And then I assume most of you have drawn out some favorite molecule. And so this quarter we do want to try to pay more attention to the geometry. So I drew these 2 hydrogens in the plane of the board. Then remember we have our wedge here, so our fat shaded here to show that it's coming out of the plane of the board. And then our dashed line is showing that our hydrogen is behind the plane of the board. And so, right, again, our typical tetrahedral model. So you can show that. Let me see if I can pull up our symmetry gallery. And so obviously tetrahedral shape, so they have a special tetrahedral symmetry. Again, that's a bit beyond the scope of this class, but you can see these are highly symmetrical. So they have all sorts of C3 rotations by every axis. So you can see that. And then also C2 rotations. Again, that just means symmetry. So highly symmetric. So good. So again, we want to say our electron geometry. So what's our electron geometry for this one? Tetrahedral, excellent. And then again, for this case, since it's all atoms, our electron geometry and molecular geometry are the same. So tetrahedral as well. Good. And so let's just look at some other compounds for fun. And so I think I've made this comment before. I'll make it again just because I don't understand what they're trying to say with this statement. So they have this statement here that it fails for transition metal compounds, but I don't really feel that that's true. And so we can make, so nickel. This is one of my favorite compounds. So nickel tetracarbonyl. And one of the favorite compounds I'll never work with. And so again, you would not want to work with this compound because it is highly toxic. And so these COs are bound relatively loosely to our nickel. And again, they're bound at this carbon, right? If you remember kind of from last quarter, with our CO structure, right, we found that we actually had a good Lewis dot structure with a negative charge on the carbon, again indicating our reactivity. I'm also drawing them with the arrow because I'm trying to show that these bonds are actually dative, meaning that carbon is donating both of its electrons to nickel here. And so my point in showing this is that it does still work for metallic species. So yes, this does have a tetrahedral geometry. But like I was saying, this compound is highly toxic. So why it's toxic? It's a liquid. It's a heavy liquid, so meaning your fume hood is not sufficient enough to keep it in the fume hood. So it would slowly waft out. And then if you were to breathe it in, obviously the CO2, or the CO, excuse me, would not be good for you. But then the nickel would plate out in your lungs, which would create additional toxicity. So very toxic compound. And believe me, I wanted to work with it. I was not allowed to. Because there was no way the engineering controls would allow for it. You would also have to, like, you can't work with it in a fume hood, or excuse me, a glove box. Most glove boxes are positive pressure, at least the ones that I worked with, so you would need like a special negative pressure glove box. So anyways, never got to work with that one. Let's try another one, again, just to kind of show our geometry. So see if you can draw out phosphate. So remember, that's our polyatomic ion. -3 charge on that, so see if you can remember how to keep track of your electrons. So see if you can draw that out. Yeah, PO4, 3 minus. So I'm seeing some good structures. Just double check. I think people are just trying to get those formal charges all squared away. So the best structure should probably have one double bond for your phosphate, and then you end up putting your formal charges on our oxygens. And then I'm not really doing a great job of showing 3D with this structure. So that's always kind of the tricky part too with these structures, is like, do you show electron and connectivity better, or do you try to show the 3D? And so obviously, right, you could also kind of make this dash and this, or excuse me, wedge and this dash, if that makes you feel better. Yeah.
The double bond preferred to be on the top, or could it be in other areas?
You could move the double bond around, but I would probably stick it either here or here just to keep it like linear, so it's not like a sticking out double bond. Not that that's like incorrect, but just trying to like keep with, you know, typical orientation. Yeah, but again, like not required, right? Because you could totally like rotate this around, and obviously it's symmetrical. And then kind of the, again, the point is to show, right, we have this double bond, but don't let that confuse you. It's still sp3 hybridized, right? Still tetrahedral. Oh, thank you. So good. So yeah, make sure you include your formal charges. And then you could do single bonds, but then you have to have a formal charge on phosphorus of +1. All right, let's try. Does this make sense? Sorry, before we keep moving. Questions? All right, so we're still with our 4-electron group. But now let's look at our next kind of classic example. So AX3E. So right, that would be taking our methane and popping one off. What is that typically? What compound is that? What has this geometry? Ammonia, yay! So ammonia, yes, is our classic compound. So NH3. And then you can sketch that out. And so this is good too. Again, right, we want to see how our structure leads to reactivity. So we have, right, these 2 electrons on nitrogen. Those are ready to attack potentially, and we will see that in terms of reactivity. And later, even with acid-base chemistry. So then going back to our little cheat sheet. So what's our molecular geometry for ammonia? You can, of course, read it there. But it also, right, it does look like that shape, right? Chemists are not the most creative. So what's the geometry? So trigonal pyramidal, exactly. And so that is our molecular geometry. And then still is going to be tetrahedral, right, for the electron geometry. Again, for that sp3 hybridization. So still sp3 hybridized. So then our electron geometry is tetrahedral. Yeah, so it's just referring to the shape, right, of the electrons and then also where your lone pair is occupying. So that's all that we're imagining. And again, right, this is prime for reactivity. And so you see this, right, we've kind of seen this. This is from, I don't know if people remember this from last year. There's these compounds. So nitrogen and boron. People like to do research with them because of exactly what we're seeing, right? So earlier we saw, well, boron tends to be typically electron deficient, and so that makes it really reactive, and it wants to obviously gain or accept some electrons. And then nitrogen, right, has those 2 lone pairs. So again, we're going to see how ammonia is reactive because of those 2 lone pairs. But then nitrogen and boron typically do kind of react or want to react and get to this scenario. And so this is a whole vein of research, basically called frustrated Lewis pairs, where you have somebody that wants to give electrons and somebody that wants to accept them, and you try to take advantage of that, obviously, reactivity. And so then we'll continue with our next one in our example. So what's our classic example of our bent sp3 hybridized? What do we say? Yep, H2O, perfect. And so sketch that out. And again, right, so we just take our ammonia, pluck off another hydrogen, so that gives us, right, the correct geometry. And so then if we go to our little cheat sheet, so this is why water, right, we typically say that it has an angle of 104.5. And again, now you have two lone pairs, kind of really putting these two other hydrogens or atoms together. So again, minimizing our distance. Again, in research, right, you might want to look for any sort of distortions in this typical angle. And so still sp3 hybridized. And then, so what's my electron geometry again? So tetrahedral. And then what's our shape now, or geometry? What did you say? Now it's just regular vent. So yeah, bent. And so this is like, I don't know, normal bent. Usually it doesn't have any qualifiers if it's just our sp3 hybridized bent. But again, sometimes you may refer to the angle of it. Questions? Make sense so far? All right, so let's start to look at our higher orders of symmetry or hybridization. So looking at 5 electron pairs. Make a new page here. And so what's kind of confusing now is our name for our hybridization. And so now, right, we call our hybridization sp3d now for 5 electron pairs. But what's kind of confusing, and if you remember to obviously my small rant last quarter, so now I'll recap it for everybody since it's very important. And so it goes back to why we see hypervalent structures pass this row, right? So again, if you remember from last quarter, it's truly a size argument as to why they experience hypervalent orbitals. But then, right, we see erroneously in textbooks where it says it invokes the d orbitals. Well, this is part of where this confusion starts to arise because we call it sp3d hybridized, but now this is really just a reference to the shape of it. And yeah, so kind of an aside. So really what we would do is like mathematically find out all the combinations. And so really they're still in line with our p orbitals, and our p orbitals are doing all the interacting. But yeah, so now the d refers to the shape, and so that's kind of confusing for people. But then we can still count this and use it to figure out how many lobes. So right, we have our s, our 3 p's, so that's 4, and then a d. But right, we're really not mixing a d though. So just keep that in mind. It's like this is now just like mathematical representations of our orbitals. And it might make more sense if I kind of draw this out like so. Because what you want to get is like your mathematical combinations of this. And well, hopefully I don't lose people. And so what I'm trying to say is this is our fully symmetric view, right? So they're all the same shading. So same shading, fully symmetric. Yeah, exactly. So that's our geometry. And so again, that refers to the shape. So right, you have these 2 lobes. So again, so they're primed in the z-axis, like she was saying. And then right, we have our kind of trigonal planar in the middle. So our 1, 2, 3 lobes, like that. But I'm drawing this like so we can see how they would actually be mathematically. Because I kind of feel like this makes more sense. And if it doesn't, you can like flag me down. But so basically we're saying this is a fully symmetric one, But okay, well, how do the p orbitals come into play? Well, let's look at this. We have pz, and we see that it's in prime interaction. So the top two are the only ones that matter, right? So the middle ones are irrelevant, what their shading is, because they're either way they're feeling half dark and half light. So it cancels out, right? Any positive or negative interaction. So that's irrelevant. And we could draw these little sticks to show that it is irrelevant. But then the mathematical representation that is relevant is that shaded and unshaded. So basically opposite shading to match with the P. Now let's see this repeated. And so now I'm going to go, let's do X in and out. So PX in and out of the plane of the board. And so that means, oops, that right, these are irrelevant because it's going in and out. So it doesn't matter what the shading is, right? It feels, again, the same positive and negative. So that's irrelevant. This is irrelevant, right? Because it's in the middle. Again, it feels the same positive and negative interaction. But then you have these two that are in line. And so, right, shaded. So if this is shaded, that has to be shaded so that they're, again, interacting and bonding positively. And then their last one, and so now I'm going to call PY going across. And this one, I think, is a little easier to see how it lines up. So again, these two are irrelevant, right? Same positive and negative interactions. But then we have this ball that's in line with PY. And then these two here, unshaded, again, would interact favorably. So all that was to just show you how we only invoke p orbitals, right? So we do not invoke d orbitals. P is perfectly fine. Yes?
I'm kind of confused on how it's hybridized with the s orbitals when we've been focusing so much on the t orbitals. Like, what role do the s orbitals play in this interaction or hybridization?
Well, the s orbital would be primarily about what this one is centered in, right? So s would be one big circle. So then fully symmetric would be all the same, unshaded in this case. But yeah, but it really just refers to the shape, right? So when we're talking about sp3d, like that's why I'm like, kind of forget what we were talking about. But now it's just this like 5-lobed shape. And then, yeah, you could get into, like I said, like the S is primarily what's interacting with this symmetry, but it's really math, right? So all this, and I'm not doing the mathematical combination right now. Like that's a separate course in itself where you like figure out the irreducible representations of all these mathematically. But all I'm trying to show you is like pictorially, we don't have to get into the math even. It's just like we can kind of see it, right? So the X is going, or excuse me, PZ is up and down, so we have to have, right, one unshaded, one shaded, so it looks like a PZ, right? And again, everything else that's kind of in the middle has the same negative and positive interactions, and you just kind of repeat that. So I'm just proving that we don't need Ds. Does that kind of make sense? I'm not trying to like lose people either, but sorry, I also get like overexcited about this topic because, like I said, this is my bread and butter here. But let's look at our typical compound then for this. So starting with AX5. And so phosphorus pentachloride is typically one. So go ahead and draw out the shape. Just practice drawing out your Lewis dot structure now. So I pulled up both our gallery here so we can kind of see. So obviously this is PCL5, and again we can kind of see the principal rotation axis. So right, this is Z, their highest order of rotation. And then, there we go. So looking at our rotations. So you can just kind of play with that. And then, so this is a good one to practice kind of drawing the 3D on it. So again, these two chlorines, right, are along our Z axis. And then again, as best as you can, kind of drawing out the trigonal planar middle here. So you can draw your dashed line to show it going back, wedge going forward. Oops. So something like this. Again, filling in all your electrons. And so again, our hybridization is sp3d, once again referring to only the shape, right? We're not actually mixing d orbitals, so kind of confusing. And so what's our geometry then? So check out your cheat sheet. Yeah, so trigonal, bipyramidal, right? And you can see that, so that makes sense, right? You have one pyramid and another pyramid, so bipyramidal. So looks good there. And so for this case, again, right, all filled in, both the electron and molecular geometry would be the same of our trigonal bipyramidal. All right, so let's try some other Lewis dot structures. So see if you can draw out the structure for SF4. What do you get for it? Yeah, draw.
It shows them all on around the center, or like the X, Y axis. How come they're not on the Z axis like this one is? Like if you had two, how come they're not, the lone pairs aren't here ever?
It's
Always
just
around
like
the center?
typical, yeah, their geometry. It just depends on like this shape, but yeah, that's like what typically happens. Okay, I think I saw one good structure. Make sure you count your electrons on this one. So this is a good one to just kind of double check our electron bookkeeping. So we have 6 from sulfur and then fluorine. So 7 times 4, Right, so we should have 34 electrons. Did I do that correctly? Double check my math. Okay, good. So then, right, filling them in. And I'm going to cheat only because I know what it looks like. So then counting our electrons, so eight times 4, so 32, right? But then we have 2 left over. And so then you want to put those last 2 on the sulfur. And so we should have a structure that looks like so. And I didn't want to give it away. And so yes, this is then our AX4E, right? So just taking our trigonal pyramidal and then popping off, right, our bonding atoms. So, right, that's representing our lone pair of electrons. Obviously, there's going to be a small bit of distortion as well. So you can kind of see that they don't really put a exact measure on that, unfortunately. But, right, you are going to have a little bit of distortion where it's going to be a little bit less than 180. And this is probably also going to be closer to probably like 119 or so. And so we may see that today in lab with our modeling. But yeah, it typically does take off from this side. So typically it bonds along our z-axis, so that's why you see it removed from that side with our geometry. And then, so what's the name of our geometry for this one? So seesaw, and you might see other names for it. So seesaw or sawhorse or something. Right, implying that this is a fulcrum that this can kind of teeter-totter on, or yeah, I don't know if anybody would ever use that. And still sp3 dehybridized though. And then that means our electron geometry is what again? Excellent, trigonal bipyramidal. And then again, obviously this is our molecular geometry with our seesaw, sawhorse. Questions on that one? Yeah, I mean, that's pretty typical of sulfur, right? So it's not out of the question. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, right, we see that 10 and 12 with sulfur and phosphorus. And that is a good point to note, though. So, yes, sulfur does feel 10 valence electrons there. So, good to identify. All right, let's see if you can draw the Lewis dot structure. These start to get interesting. Let's try IF3. Sometimes if people are really mean, they just do like I4, but I'm not sure that I4 really exists, so that's why I like calling it IF3. Looks good. See a lot of good ones for this one. I thought this would stump you more. So we can do, right, so they all have 7 valence electrons, so 7 times 4, so 28 electrons. And then I saw good structures, and so you can kind of draw out this T-shaped looking thing. And then obviously fill in your electrons. So 8 times 3 is 24, and then you would find, right, you would need 2 lone pairs, and you might want to circle them just to, again, kind of emphasize their occupying space and where they're occupying space. And so, yes, so right now we just pluck off another one, so that gives us, again, our T shape, so maximized for geometry. And then I like this because, again, easy geometry. So I gave it away, but our molecular geometry is then T-shaped. Easy enough to remember.
Why is it T-shaped instead of trigonal planar?
Because trigonal planar, right, would be more even. So looking at this, right, trigonal planar has even 120 between all 3. But this is T, right, because it has 2 lone pairs there, as opposed to trigonal planar having none. So these are occupying space and then forcing it into that T position.
Can take up the axial positions?
Of the z-axis.
Yeah, then they'd be farther apart, wouldn't they?
Typically, so the z-axis tends to get like elongated, so it tends to be more favorable geometrically. But yeah, it's just the best way to fit around, because you have to fit around 5 electron groups still, right? So even though you've removed kind of 2 atoms, those lone pairs are still occupying space, so that's why it's T-shaped, yeah. And then forcing us to then, right, kind of a 90-degree angle there. Again, you might see distortion. That's probably pretty typical. And then again, electron geometry is still what again? So trigonal bipyramidal. And I'll put sp3 hybridized again still, just so we remember. Okay. Let's see if we can fit. Oh, and so this would be AX3, E2. And so now let's try, well, you can figure out the next one in the pattern. So AX2, E3. But our typical compound for that is xenon difluoride. So go ahead, see if you can draw out the Lewis dot structure for xenon difluoride, and of course include all the appropriate lone pairs. Okay, I'm mainly seeing good structures. Just watch, again, the shape on this. So, right, again, we're starting with our T-shaped, essentially, and pulling off our last pair of electrons. So now we have, right, xenon difluoride. And again, we have our 3 lone pairs all around. And so we want to show that. And so what's our geometry then? Molecular geometry. Linear. And so, yes. And then obviously, right, don't confuse it with our SP linear. And so this is still sp3d hybridized. So now linear, and then electron geometry, back to our trigonal bipyramidal. So that looks good. All right, let's see if we can, I don't know if that will finish with our 6 electron pair group, but we'll start. So our 6 electron pair. So what's one of our typical compounds for this? Do we remember? So that will be in the 6 electron pair group. So I'll put it down lower. But which one? What has 6 things attached to it? What's your typical compound?
SF6.
Yes. So SF6, right? So remember the sulfur hexafluoride. So see if you can draw that out. But remember, that's also the compound used. Sometimes people breathe it in and it makes your voice lower as opposed to, right, helium that makes it higher. So obviously this is more dense, hence why lower your voice. So this is a good one to, again, kind of just practice drawing. And then you could draw it like so with our dash and our wedges, right, to try to show our geometry and emphasize, right, that these 4 fluorines are kind of in our square plane there, coming out of the board. These are coming behind the board. And then what's this geometry called? So octahedral. And then, right, hybridization, so sp3d2. And again, this is confusing because now this is just referring to the shape, again, of our 6 lobes. So looks like so. And this one tracks a little better with kind of the p orbitals if we were to do kind of that similar exercise, right? I'll do it a little faster, but we can see, right, the pz, you have 2 of your atoms fall right along that pz line. And then, right, these 2 fall along py. So, right, this could be py here and px. And so, again, that would mean that you could draw it like so. again, in line, this would be your mathematical representation, and then again, px. So your mathematical representation of your orbitals, or your atoms, and how they'll interact with your orbitals right on sulfur. So again, all we're showing here is we did not actually invoke any d orbitals, but our hybridization, again, refers to our shape. So it makes a 6-membered lobe that can then interact with our 6 atoms here. Questions about this one? All right, let's see if we can draw one more real quick. I know we're running out of time. Try this one. So bromine pentachloride. So count your electrons. So this is a good one to maybe count our electrons, right? So bromine and chlorine all have 7, so 6 times 7. So 42 electrons, right? So then we can start just connecting them. Sorry, I drew a little cockeyed. And then, so 1, 2, 3, 4, 5. So 5 times 8 is 40, right? So now 2 left over, so those 2 go on the bromine, which is kind of what we'd expect from our lecture pattern so far. Oh, I'll get rid of xenon. We'll come back to him tomorrow. So then this is AX5E. And so we're kind of running out of time. So we'll look at that. So this is square pyramidal, but we'll probably come back to this, like I said, on Thursday. So we'll kind of leave off here. So we'll pick back up with this bromine pentachloride, like I said, on Thursday. So again, looking at this square pyramidal geometry. But we'll finish off with this, and then we'll keep kind of drawing our shapes, practice our hybridization on Thursday, and then have our little mini quiz, or welcome quiz. It's not a quiz that you need to study for.
So the molecular geometry is square pyramidal.
Yeah.
The electron geometry, is it still octahedral?
Yep. Any questions online?
Find all the old things that you gave us, because I completely forgot to bring my periodic table.
Oh, I forgot to print new ones. That's right. I'll print new ones. All right, I'm going to end this.